Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 5, Analytical Applications of Differentiation. Today's topic is 5.6, where we're determining concavity of functions over their domains. Enjoy today's notes.
All right, for the 5.6 video on determining concavity, we're going to start with what concavity is. So we talked about this back in chapter 4, but concavity, says the state or quality of being concave. In general, concavity refers to the curvature. It is about the curvature of a graph or of a function at a particular point. So in general, we talk about a function being concave up or concave down. Concave up opens upward. We say that it opens upward, and it is U-shaped like this, while something that's concave down opens downward. And I would say, while we said that concave up is like a U, opening downward is more like an N. And so it's essentially the idea of like a parabola opening downwards. Now, not every function on an interval has concavity. We would say that, for example, a straight line is neither curved upward or downward. We would say that this has no concavity. And a function, depending upon the interval, could have, things that are concave up or concave down. For example, if we think about, just even a basic cubic function, if we think about the function like y is equal to x cubed, we have a function that essentially looks like this. And what we notice here is that on this green part here, that this part is U-shaped, or rather N-shaped. It is curving downward. We see that essentially it looks like that downward parabola. It's curving downward. So this is a part that is concave down, while this part that's up here, which I'll put in purple, is more U-shaped, and that is concave up. So what we can see is that that a given function can be concave down and concave up on different parts of its interval. Any given interval needs to be one or the other. And while we're at it, I'm going to introduce a new definition, which is this idea of what is called a point of inflection. So this point right here, this exact moment, which I guess I'll like highlight in maybe orange, this exact spot where the concavity changed from being concave down to concave up is what's called a point of inflection. It's a point of inflection. And in general, any spot on a graph where the concavity changes from being either up or down to down or up is what we refer to as a point of inflection. We'll talk more about how to find those and why they're useful, but in general, a place where concavity changes is what's called that point of inflection. All right, so let's take a look. If a function is concave up like a parabola, what is f prime doing? So this is a function, a graph of f of x, and we're talking about what f prime is doing. So we notice that f prime, again, is going to be our tangent lines. And so if I draw a tangent line over here, we notice that the slope, we notice that f prime is negative, that the slope is negative of that tangent line. We notice down here at the vertex of this, parabola-looking shape, that the slope is 0, so f prime is equal to 0. And then we notice if we pick a spot here on the right side of the graph, that the tangent line has a positive slope, so f prime is greater than 0. So if a function is concave up like a parabola, what is f prime doing? Well, f prime of x goes from negative to 0 to positive. So we saw, again, looking from left to right, that we start with a negative slope, then a slope of 0, then a positive slope. Specifically, f prime of x went from negative to 0 to positive there. So if f prime of x, f of x is concave up, then we can say that f prime of x is increasing. It is increasing. Because we noticed again, it was negative, then 0, then positive. It is increasing that f prime for this function. And similarly, if this were concave down, we would have the same idea, except it would be going in reverse. If f is concave down, then we would say that f prime is decreasing. And we can conclude that, this leads us to the following, that if we have the second derivative is positive, that, again, the second derivative is the derivative of the first derivative. If the first derivative is increasing, that means the second derivative is positive. So if it's concave up, that means the first derivative is increasing, and that would mean the second derivative is positive. So we can conclude that if the second derivative is positive, that means that f is concave up. It means that the original function is concave up. Similarly, since if f is concave down and then f prime is decreasing, that would mean the second derivative, right? If f prime is decreasing, the second derivative needs to be negative. And so therefore, if the second derivative is negative, that means that f has to be concave up. This is a cool conclusion, and I'm going to highlight this because this is a big idea here, that we can use the second derivative to determine whether or not a function is concave up or concave down. Obviously, if you were looking at the function, you might be able to see that curvature, but sometimes we have information about the derivative or the second derivative when we don't know about the original function itself. So it is very useful for us to be able to say, hey, if I have information about the second derivative, I can tell that f of x is either concave up or concave down. This over here is a typo. So let me fix that. If f double prime is negative, that means that f is concave down. So sorry about that. So positive, concave up, second derivative negative, concave down. Great. Looking at this graph of sine of x, we can see sort of some different parts of curvature here. So I'm going to just use two different colors. We can see that this part down here and down here are parts that are concave up, and I can tell you here that the second derivative on those intervals would have to be positive if we were to do that. And these parts up here on the top, where we see that it is more n-shaped, has that curvature curving downwards, those are places where the second derivative would need to be negative, would be here and here. Useful to know. All right. Number one, find the intervals of concavity for f of x is equal to 1/4 x to the fourth minus 6x squared plus x minus 3. All right, so if we're going to find the intervals of concavity, we need the second derivative. So let's find that. The first derivative of this function is going to be x to the third minus 12x plus 1 if we use the power rule. The derivative of that is what we refer to as the second derivative. That's going to be 3x squared. Looks like minus 12. So 3x squared minus 12. Now, I am interested in finding these places where the second derivative is 0, because it's going to give me some indications of where the function might be switching from positive to negative. These are possible places where we have points of inflection. So I'm going to take that f double prime of x, and I'm going to set it equal to 0 to find possible points of inflection. Possible places where the second derivative is going to change sign, and that if it does change sign, then it would be a point of inflection. So here we're going to say 3x squared minus 12 is equal to 0. I'll factor a 3 out, so 3 times x squared minus 4 is equal to 0, and so that we have 3 times x plus 2 times x minus 2 is 0, and that would mean that x has to equal negative 2 or 2. So these are possible points of inflection, would be negative 2 or 2. Now, similar to what we've done in previous lessons, what I'm going to do is I'm going to make a sign chart. I'm going to make a sign chart, but for this one, I'm going to use the second derivative. So my sign chart here is going to have x and f double prime of x, and our two x values that we care about are negative 2 and 2. And as usual, I want to write for the x values the domain around these x values that we've got. So for this one, going from negative infinity all the way to negative 2, then we've got from negative 2 all the way to positive 2, and then from 2 all the way up to infinity for this. We already know the second derivative values at negative 2 and 2 because we've found those by setting the second derivative equal to 0. And so those are the values that make that equal to 0. And then what we then need to do is find the signs of each of these second derivatives on these intervals. Again, we've talked about this before in previous videos, but maybe you're using like a test point. Maybe I'm plugging in like -3. Maybe here I'm plugging in 0. Maybe here I'm plugging in 3. Plugging those into our second derivative equation. And again, all I really care about here is the function positive or negative? Is the second derivative positive or negative on that interval? We're talking about the signs of that second derivative. Now, if we do that, if we plug -3 in, that -3 is going to get squared, so making it positive, and then that number is going to be multiplied by 3 and subtracting 12. So we're going to have a positive number there. And then if we plug in 0, that would go to 0, and we'd subtract 12, so we'd have a negative value here. And then if we plugged in a larger number, for example, say like +3 or like 5 or 10, this is going to end up being positive here for this one. So we notice that the second derivative is going from positive to negative to positive. So what can we conclude? I'm going to quickly erase these x values. We can conclude that the original function, so I know that f of x has to be concave up on this interval, then concave down on this interval, then concave up on this interval. Again, because if the second derivative is positive, it's concave up, and if the second derivative is negative, it's concave down. So let's write our final answer for this, our statement with a conclusion. So we know that f of x is concave up on -∞ to -2, that interval of x values, and from 2 to infinity, since f double prime of x is positive. And while I'm at it, I'll say that f of x is concave down on the interval from -2 to 2, since f double prime of x is negative. So this would be my conclusion statement about what I know and why I know it. So I know where it's concave up because of the second derivative, and I know where it's concave down because of the second derivative as well. All right, so points of inflection, sort of a formal definition that we've got here. Point of inflection, a point of inflection of f, or so there is a point of inflection of f at x equals c if f of c is defined and f double prime changes signs at x equals c. So not only does there have to be a place where f of c is defined, but we also need to have f double prime changing signs at that value. So in other words, a point of inflection is where a graph changes concavity. It's where it changes concavity. So specifically here, we can go back up to this sine graph that we had here. And in fact, each of these places, these x values where the graph change from concave down to concave up would be our point of inflection. And I'll just write that once. This is a point of inflection. We've got a point of inflection here, and that's also a point of inflection. And if we were to extend it, it looks like that would be as well, and maybe that would be as well. We know obviously the sine of x graph goes forever in its domain to the left and to the right, so this would have an infinite amount of points of inflection. There'd be one every single point where it crosses the x-axis because the concavity would change from being concave up to concave down. Great. Cool. Let's go. Two common mistakes when finding the point of inflection. So what are those two common mistakes? So one of them is assuming that simply the second derivative being equal to 0 means that there is a point of inflection. That is not true, right? It's not just that the second derivative is equal to 0. We need to know for sure that the sign of the second derivative must also change. You must show that that sign changes, because I could have a point where that second derivative is 0, but the sign doesn't change, and so therefore the concavity would not change either. The other is that the second derivative not existing. So if the second derivative of x does not exist, people assume that that means that there's no point of inflection. That is not true either. because there might be a reason why that doesn't exist. So for example, let's imagine we've got a function that looks like this. Now we know from earlier this year that this graph has a feature which is what's called a cusp. And obviously, you know, the function is defined at each of these values. But when we get to here, we know that the first derivative doesn't exist. We know that we cannot draw a tangent line. We don't know how we would draw it. So at a cusp, the first derivative doesn't exist. And so since the first derivative doesn't exist, it can't be changing, which means the second derivative would not exist there either. So this is an example where the second derivative does not exist, but there is a change in concavity, because we notice here that on the left, it is concave up, right? It's curving upwards. And then we have this point where the first and second derivatives do not exist, and then suddenly the function is going concave down. So do not assume that if the second derivative does not exist, that there's no point of inflection. In general, the best case scenario is if I'm looking for a point of inflection, I am looking for places where f double prime of x is equal to 0 or does not exist. I'm looking for those because these are possible points of inflection. Possible points of inflection are there. And then once I have these possible points of inflection, I'm going to then go ahead and look for sign changes. So then I'm going to look for sign changes of f double prime of x. Because then once the sign changes around those possible points of inflection, it's either yes, going to be a point of inflection, or no, not going to be a point of inflection. Great, let's move on to number 2. Given the graph of f prime, so this is a graph of f prime, find the points of inflection and state the intervals of concavity. So I'm assuming, it doesn't say explicitly in this problem, but I'm assuming we're talking about finding the points of inflection of f of x. So not the points of inflection of f prime. So if that's the case, we know to find the points of inflection of f of x, we need to look at the second derivative. But we have the first derivative here. So what would be our second derivative? Our second derivative would be the slope of this graph, right? It's the derivative of this graph. And so the slope would be the slope of the tangent line at a given point. So what I notice here is the slope of this interval going from -4 to -1 looks like it has a negative slope. It has a negative slope. Then at -1 all the way up to +1, it looks like it has a positive slope. And then I see a negative slope from 1 to 2, and then a positive slope again there. So because the slope here is negative, I know that f double prime of x has to be negative on both this interval here and on this one over here, while I also know that f double prime of x has to be positive on this part of the graph here and on this part of the graph here, where these slopes are positive. So given that, we can say that f of x is concave down. It's concave down on the intervals from -4 to -1 and from 1 to 2, since f double prime of x is negative. And we can also say that f of x is concave up on these two intervals from -1 to +1 and from 1 to 2, since the second derivative is positive on those intervals. Now, in conclusion, just in general, when we're looking at this f prime of x graph, to think about the second derivative, we're trying to look to see where f prime of x is increasing or decreasing. Because if it's increasing, then we know that f double prime of x is positive. And if it's decreasing, we know that f double prime of x has to be negative. So that's the general gist if we're looking at that f prime graph. What happens, though, in number 3 if we're looking at a graph of f double prime of x? How do we find the points of inflection and state the intervals of concavity? Well, the second derivative here is giving us the outputs of the second derivative function from our original function. So really here, all I am caring about is where is this function above the x-axis or below the x-axis? Where is the output above the x-axis or below? Here, the output is above the x-axis and above the x-axis. That means if the output of the second derivative is positive, well, we know on those intervals that, that f of x would have to be concave up. So f of x is concave up on the intervals from, looks like, -infinity to -3, and from x equals 1 to 3 here, since the output of f double prime of x is positive. We can do the same idea here with the second derivative of being concave down by taking a look where it's below the x-axis. And so we see this interval here and this interval there, where the output of the second derivative is negative. So that interval is, looks like, from -3 to +1, and from 3 going forever, since that arrow is there, to infinity. And that is since f double prime of x is negative on that interval. So slightly different in the way that we look at these graphs. Here, when we're looking at f prime, we're looking at the slope of the graph. Is the slope negative or positive? Here in f double prime, since we care about whether f double prime is positive or negative, we're simply looking at the output of the function, and we're seeing if it's above the x-axis or below the x-axis. And that gives us information about f of x, a function here in neither of these cases that we know anything about except for the derivative and second derivative of it. So that's pretty interesting that we can make some conclusions about f of x, even though we don't know, what that graph looks like. Cool. Number 4, does the line tangent to the graph of f of x, so does the line tangent to the graph of f of x equals f of x equals x e to the negative x at x equals 1 lie above or below the graph of f? Okay, this is a throwback to chapter 4. So back in chapter 4, actually, the 4.6 lesson, we talked about concavity and tangent lines. Concavity and tangent lines. Really quickly here, the idea is that if you know a function is concave up, any tangent line that you draw on it will be below it. So functions that are concave up, tangent lines give underestimates if it's concave up. Similarly, any concave down function, if you draw a tangent line any part on that concave down function, is going to be above it. So therefore, something that is concave down is going to naturally give an overestimate because that tangent line is going to be above the actual function. So that's our review from 4.6. Let's take a look at it with this specific problem. If we're going to determine whether it's above or below, I need to know the concavity of this function. Back in 4.6, they told us the concavity, and here they're not, because now we know how to find the concavity, and that is by looking at the second derivative of the function. So what do we need to do here? Well, if we got the first derivative, rather the original function, we need to find the first derivative first. Here I'm seeing x times e to the negative x, so I have to use my product rule here. This is 1 times e to the negative x plus x times e to the negative x times -1. So a mixture here of the product rule and the chain rule. What I'm going to do to simplify this is I'm going to just see how we can maybe factor. And so this is x e to the negative x. I notice that both of those have e to the negative x's here. Actually, I'll just leave that the way it is. I think this is going to be fine here. So that's f prime. And if we take the derivative of that, we're going to call that the second derivative. Here, e to the negative x, the derivative of that, it's just by itself. So this is e to the negative x times the derivative of negative x, which is -1. And then we've got minus here, I'll go in green, x e to the negative x, which was what our original function was. And so we've already found that derivative. It's essentially what's right here. So I'll just put in parentheses e to the negative x minus x e to the negative x. Okay, well, let's try to simplify here a little bit. This looks like this is negative e to the negative x minus another e to the negative x. What I'm doing here is I'm distributing this negative sign to each term on the inside. So then we've got a plus x e to the negative x. So what do we have together? I'm seeing a negative 2e to the negative x plus x e to the negative x. Both of these have those e to the negative x's out, so I'm going to factor those in front. So e to the negative x times negative 2 plus x would be that second derivative. Okay, well, where is this thing going to be, where is this thing going to have a possible point of inflection? So possible points of inflection here would be, well, actually, no. They're talking about specifically at x equals 1. Sorry about that. So since they're talking about specifically at x equals 1, I'm curious what happens to this at 1. So f double prime of 1 is e to the negative 1 times negative 2 plus 1. So that is 1 over e times negative 1 or negative 1 over e. Now, I actually don't care about the value itself. All I care about is the fact that this is negative. Because since the second derivative is negative, we can conclude that the second derivative, since the second derivative is negative, that the original function has to be concave down. So my conclusion here, I'll scroll down even though this is the practice. Since f double prime of 1 is negative, we know f of x is concave down when x equals 1. And this would be our conclusion for that final problem. Great. So that is going to be it for number 4, and that's it for our lesson for today. As usual, we've got some practice. We've got some test prep here at the bottom. Try these out. Check your answers with the posted work. Come to class with any questions that you've got, and good luck on your mastery check. Have a great rest of your day.